now you have a series LCR circuit. Okay, see, in a series LCR circuit, what was happening? So in a resistance, the EMF and current were in phase, and then in inductor, the EMF was leading the current by pi by 2, and in a capacitor, EMF was lagging the current by pi by 2, correct? So we saw these three. Now suppose, let's say we start increasing the frequency. Okay, so let's say what we have is let's say 100 hertz. Okay, so from 100 hertz, so I increase to 1000 hertz. So remember XL, the inductive reactance, and XC, the capacitive reactance. Now inductive reactance was what? Omega into L, correct? Or 2 pi F into L. Now same way, capacitive reactance will be 1 by 2 pi Fc, correct? Now as the value of F is increasing, XL value will keep on increasing, correct? And XC will keep on decreasing. So one is increasing, the other keeps on decreasing. The resistance, it's not gonna matter, right? Now from 1000 hertz, again I increase to, let's say, 10,000 hertz. So still XL will keep on increasing, XC will decrease. Now suppose, let's say I do the other way around now. That means I keep on decreasing. Let's say from 100 hertz I come down to 10 hertz. Then XL will decrease and XC will increase, correct? So what's happening here? So as I change the frequency, one is increasing, other is decreasing, and the other way around again, correct? Now see, suppose, let's say I pass a direct current. Okay, so for a direct current, the frequency is 0. So XL becomes 0, that is 2 pi FL, meaning an inductor is basically, we consider it to be a coil, correct? So an inductor will have 0 inductive reactance. That means it acts like a straight wire. Whereas a capacitor, see, capacitive reactance will become 1 over 0, meaning capacitive reactance becomes infinite. So a capacitor blocks a direct current. Okay, so this is what it means. So if XC becomes infinite, that means the capacitor blocks the direct current. Okay, now see, what we are looking at is, depending on the frequency, the inductive reactance and capacitive reactance will change, correct? So let's say at certain frequency, let's say omega naught, we have XL is equal to XC. Okay, so what we can say is omega naught L is equal to 1 by omega naught C. Okay, so we'll get omega naught is equal to 1 by root of LC, because cross multiplying you will get this. Now this omega naught is what we call as resonating frequency. Okay, or this condition is called as resonance. Alright, so in resonance, see, there are certain points which you guys have to know. First point is, in resonance, the whole LCR circuit acts like a pure resistive circuit, because XL and XC are equal, so they cancel out each other. Okay, this is first point. Second point, in a series LCR circuit at resonance, the current will be maximum. Okay, and the current is given by E divided by R. Alright, and the third point, so see how we have this impedance of a series LCR. Remember, root of R square plus XL minus XC whole square. So this impedance of the LCR circuit will be just R, because XL and XC are equal. Okay, so remember this point, at resonance, the whole circuit acts like a pure resistive circuit. The current is maximum and impedance is minimum. Okay, and the resonating frequency omega naught is 1 by root of LC, or if we need F naught, that will be 1 by 2 pi root L into C. Okay, so based on resonance, we have other terms related to it. Okay, so we'll see those things in the next video.